Hello everyone, welcome to this tutorial on running the time series trajectories package in R. Thomas Bilintoh developed this package to use a recently developed method that addresses the limitations in existing methodologies for analyzing land change dynamics. The method focuses on understanding a category's behavior over time across different locations, particularly when the time intervals are of inconsistent duration. This new method calculates the gross gains, gross losses of a site, categorizing the change into 8 possible trajectories, and then decomposing the change into 3 components: quantity, exchange, and alternations. For a detailed explanation of trajectory analysis, you can find a link in the description box. We have included links to our GitHub repository and the official repository for the time series trajectories package. In this tutorial, we will use data from the Mahakam Delta in Indonesia as an example to demonstrate how to use the package effectively. We will guide you through preparing your data before running the time series trajectories package, understanding the results generated by the package, and interpreting those results to gain meaningful insight. By the end of this tutorial, you will have the confidence and skills to use the time series trajectories package for your own analysis. So let's get started.
This section will cover installing R, RStudio, Rtools, the time series trajectories package by Bilintoh, along with some R basics that will help new users. Please utilize the section names on the progress bar to get to the part that applies to you. All links are in the description of this video. First, I will go over installing R. Starting with the posit.co link, users can go to this section of the page and click Download and Install R. Then users will pick one of these 3 links based on their operating system. I'll be using Windows for this example. First-time installers will choose Base. For the install wizard, keep all of the default options. On the rstudio.com page, we can hit the back button once to install Rtools. It's best to use Rtools 4.4 as this is the newest version. Again, keep all of the base options. Next, we can go back to the posit page to install RStudio. Windows users will click this button right here. Mac users will go down here and use this button. And Linux users will have to follow this link as it requires some extra work. We'll use all the default options again. As an overview, R is the specific programming language. RStudio is an IDE, integrated development environment. You can think of this as RStudio being a user-friendly environment to work with R. Now we can open RStudio. Sometimes RStudio won't recognize that you've installed R. However, the machine can automatically detect this, so you can leave this as is and just click OK. After opening RStudio, there are some basics you need to understand. To walk along, click File, New File, and then RScript. In R, to create a variable, you use the less than symbol followed by a hyphen. For instance, we can click the Run button. Now we have this variable, and you see it over here. To get the output, we can call the variable again, click the Run button, and you'll see down here in the console section, we have 90. Some basic buttons in R that you'll want to know is the Save button and the Run button. The Run button will always run whichever line your cursor is on. Another way to speed this up is on Windows, you can use Control-Enter, and it will also act as clicking that button. Notice the output. Now, to install the time series trajectories package, we will utilize the DevTools library. If it is not already installed, you can execute the following code. Once this red symbol on the side is gone, that means the code is done executing and you can continue. And to install the package from GitHub, we can execute the following. Users that previously installed R may see a prompt for the user to update all the packages that timeseriesTrajectories uses. If this happens, in the bottom left section, where we are in console, you'll be able to type the number 1 and hit enter. This will update all the packages. And for new R users, just to clarify, R packages can call and use other R packages within them. Another way to update packages is the bottom right box. Click Packages, then the Update button. This will show what packages that you've already installed onto your local machine that need to be updated. You can do one at a time, several at a time, or you can select all of them at once. Additionally, we'll need to install 2 more packages to run our demo since we use different data than the original Bilintoh package. They are raster and SP. All installs and updates are now complete. To follow along in our tutorial for the timeseriesTrajectories package.
Welcome to this part of the tutorial where I will be showing you the demonstration of how to run the time series trajectory analysis package in R. In this part, I assume you already have your Rtools, and RStudio installed, ready to get started with implementing the case study example that we have for you. So the first thing you will need to do is to open your RStudio development environment, get that set for yourself, and then you go to our GitHub project, and right here you simply come to code, go to SSH and copy over the link there. Once that is done, you can come back to the RStudio, go to File, New Project, and then once that is set, you come to version control. In this case, we are using Git. You go to Git and you paste that link here and create a new project. What it does is it clones over all of the project files that we use for implementing this. And that is what you can see right here. If you on the right side of the screen, you can see all of the files you need. Now, we already have the HTML file. If all you need to do is to simply view the tutorial without implementing it for yourself, you can go to your browser and open the trajectory analysis file as an HTML document. When you do that, this basically comes up for you. And in that case, you can read along and see all of the different parts with the code and the visualization of this tutorial basically available for you there. And in your case, you can decide to copy this over to a separate project, or you can decide to re-implement it and just adjust the data set. What we assume will be the case is you most likely would be faking this and just imputing your own data. So what we have implemented here in this particular document, an example we're showing you, is a case study of mangrove transition to shrimp ponds in the Markham Delta. And we basically show you how to prepare your data from whatever format it is into the format that is required for implementation in the time series analysis package from start to finish. I'm just going to go over to RStudio, and right there I can open my RMD script. That is the R Markdown script, basically, which you can adjust for your own use case. This document contains series of links and at the same time the codes that you need to implement this package. If you haven't already done so, you should install the DevTools and the time series, Bilintoh time series trajectory, which is on GitHub. So you need the DevTools to get that installed. And that way, also, you should also install Terra, and that way you can have this example to be able to run effectively. So what we have is we have a coastal habitat map. In this case, I'm just going to go over some part of this. When I load Terra, and at the same time, I can show you what the coastal habitat map is. You can either just load that into your development environment on the console and see examples of this, or you can just directly knit the markdown and get the final output we have. So in this case, I just want to show you what our coastal habitat map is and how you can get that within RStudio itself. So once you have this, you can either choose to work with this way. In this case, this is using all the settings we have, and it's showing us the different trajectories we have. What would you expect from people is to either open our HTML file directly, or you knit it here following the whatever adjustment you have. And once that is done, you should be able to have for yourself this same document we have, or a modified one, depending on your particular use case and adjustment. But remember, in your implementation, ensure that whatever data or changes you made is in the data folder and stored appropriately. And that will be it.
In this section, I will briefly explain the output maps and graphs from Thomas Bilintoh's Trajectory Analysis R package. Quick caveat: the formatting of these maps and graphs may differ depending on your version of R. The first output you will have will be a graph like this one that tells you the number of pixels of the variable you are studying there are at each time point. In this example, this graph is telling us the number of pixels that are mangrove in Mahakam deltas in Indonesia. As you can see, the time intervals here are 1999, 2014, 2018, 2020, and 2022. Take particular note of the fact that the number of mangroves increases between 2018 and 2020. The next two outputs you will get are these maps. The first one on the left shows at how many time points the variable you are studying are present at each pixel. The second map on the right shows how many times the pixels change between presence and absence of the category you are studying. These maps will help with understanding alternation, which will be explained shortly. To use any maps from this R file, you'll want to save the maps as a TIFF file, then import them into your preferred GIS program. The next map you will get will be a map like this one that shows the trajectory of each pixel. For more information on this concept and a more detailed explanation of what each trajectory is, see the explanation video made by our colleagues linked in the description. In this map, each pixel is color-coded according to its trajectory. Any pixel in white is outside the spatial extent of your study area. This trajectory is lost without alternation, denoted by the red color on this map. What this trajectory refers to are pixels that at the first time point have the interval being studied, mangoes in the example, and at the last time point do not have the variable being studied, and never gain the variable being studied after having lost it. Trajectory denoted in pink on the map show the pixels that have loss with alternation. What this trajectory means is that the pixels at the first time point have mangroves, or the variable being studied, and at the last time point do not have the variable being studied. But in between the first and last time point, there is some time interval where, after having previously lost the variable being studied, the pixel then regained that variable, only to lose it again, therefore ending with a loss overall of the category being studied. Trajectory number 3, gain without alternation, denoted by blue in this map, represents the trajectories where at the first time point there's an absence of the category being studied, and at the last time point that there's a presence of the category being studied, and there's never any shift in those pixels from having the category to not having the category. Trajectory number 4 is gain with alternation, denoted by the cyan pixels on the map. Pixels in this category have an absence of the category being studied at the first time point, and at the final time point have that category as presence for the pixel. However, during some interval in between the first and last time point, there's a transition that the pixel goes from having the category to not having the category being present. The 5th trajectory, denoted by the olive color on the map, is all alternation loss first. The pixels in this trajectory start and end with having the category being studied present on the pixels, but at some time point being observed, the pixel has an absence of the category being studied. 6th trajectory is all alternation gain first, denoted by the yellow colored pixels on the slide. Pixels in this category start and end with having the category being studied absent from the pixels, but at some time point that's being observed during the time extent, those pixels have the presence of the category being studied. The trajectory, which are the dark gray pixels on the map, is stable presence. These pixels are where the category being studied is present at all time points observed during the study time extent. Final trajectory is stable absence, denoted by the light gray color on this map. The pixels in this trajectory are where at no time point that's being observed is the category we're studying present. Next output is a graph that shows the percentage of pixels in the temporal extent during each time interval that ends with each trajectory. The graph also shows 2 lines. The top dotted line represents the average gain of mangrove over all time intervals. That is the average gain of the category being studied over all time intervals. The bottom dotted line represents the average loss of the category being studied over all time intervals. The portions of the bars over the 0 line represents the percentage of pixels that gain the category being studied during that time interval. The portions of the bars below the 0 line represent the percentage of pixels that lose the category being studied during that time interval. Output is this graph that shows the percentage of pixels in each of the 3 categories over the entire temporal extent. Those 3 categories are alternation, exchange, and quantity gain or loss. Alternation is the portion of change that derives from pixels that change more than once. Exchange is the portion of change whose pixels transition away from mangroves, while other pixels transition to mangroves during the temporal extent. This derives from 2 time points, the initial time point and the time point at the end of the temporal extent. Quantity is the net change in number of pixels of mangroves. This is the end of our tutorial for how to use Thomas Bilintoh's time series trajectory package in R. If you have any further questions, refer to the links in the description that will provide more detailed explanations of these topics, as well as the paper itself. Thank you for watching. We hope this video helped.